Hey guys, here is your intro to the integral test. And the way we're going to start this out is we're going to start out with a series that we are somewhat familiar with. 1 over n squared. So in this corner, we've got 1 over n squared as my series. And in this corner, we've got the integral of 1 over x squared. So I basically turned my a sub n term into its own little function, and we're going to compare the series to the integral. Okay? So the best way to do this is really to look at a picture. So let's get a good picture. 1 over x squared, something like this. I think we'll just wait on that. And let's see. So f of x is 1 over x squared. And we need to sort of somehow find a way to compare this integral to the series. So the way to do that is we actually use our old-fashioned method of rectangles. So I've got, let's just do a few. And let's go ahead and do the right-hand method. Okay? Not drawn to scale. And there we go. Now why would we want to do these rectangles? Because if you find the area of these rectangles, it's going to look very familiar. Let's see, base of 1, height of 1 over 1 squared. So my area is 1 over 1 squared. My area is 1 over 2 squared, right? There's my height, right? 1 over 2 squared, and my base is always going to be 1 with the way I set this up. 1 over 3 squared, 1 over 4 squared, 1 over 5 squared, etc. So, excuse me, these individual areas represent my series. If I were to list out the first few terms of this series, I'd have 1 over 1 squared, plus 1 over 2 squared, plus 1 over 3 squared, etc., etc. Okay? So these boxes, the area of these boxes, if I added them all together as far as we can go, it would resemble this, this series. Okay? So here's the connection. All of these boxes are underneath my curve. So if I were to add up the area of all the boxes, I would be less than the area underneath the curve. So this series of 1 over n squared has to be less than my integral simply because all of the boxes are below the curve. Okay, in the original way we talked about this, we would talk about this being like an underestimate. Right? If the function was decreasing and you used right-hand method, we'd always have an underestimate. There's only one little catch here with this particular example is my series and my integral. It's not a fair matchup at the moment because my integral starts at 1. So the area under my integral, or excuse me, the area represented by this integral underneath 1 over x squared is really all of this. But I haven't accounted for this one box that's kind of left over because it's on the left side of where I'm starting for my integral. So to make it a fair fight, I do need to add 1. Now, that doesn't really change the fact that this integral was going to be bigger than this series anyway, but it has to at least make it fair. Okay? So this integral, no matter what, is going to be, well, plus 1, is going to be bigger than this series. So the idea here is, remember, the ultimate goal is, does the series converge or not? Well, if we can determine whether or not this integral converges, that might give us some information about my series. If this integral converges to a particular value and this series is less than that value, well, then we can conclude that this series must converge. Okay? So let's take a look now. Focus your eyes on my integral. And we've actually done this integral before. That's why I picked it. When we first learned improper integrals, when we go from something to infinity or there ends up being some kind of infinite value involved, we used our excuse me, improper integral technique. So I'll make a little star here and we'll do it over here. Take the limit as t goes to infinity from 1 to t of 1 over x squared dx, and we can actually figure this one out. This is going to be the limit as t goes to infinity. This is x to the negative 2. So my antiderivative is going to be x to the negative 1 over negative 1 evaluated from 1 to t. Okay, and I'm still, move the mouse, still using the limit as t goes to infinity. So the limit as t goes to infinity for, this is really just negative 1 over x, right? So negative 1 over t minus negative 1 over 1. So that's the limit as t goes to infinity of negative 1 over t plus 1. And what happens as t goes to infinity for 1 over t, or even negative 1 over t, it doesn't really matter. This goes to 0, so this is 1. This improper integral evaluates to 1. So that means when I set up my inequality here, which I'll do it on this side. Keep it all on the same page here. So from my series, 1 over n squared is less than, this is going to be just 1, plus 1 is 2, right? This is just 1 plus 1, 2. So my series must be less than 2. So my integral converged. I took care of the balancing with the plus 1. It didn't matter. Even if this ended up just being 1, my series is still less than that. So my series is less than 2. I don't have the exact value for the series. I just know it must converge. So this series converges, and we will call this by the integral test. Integral test. So if your integral converges, then your series will converge. Okay, if you match them up, if you take your a sub n term and basically turn it into a function, then your series will converge if your integral converges. Okay. All right. So some of you might be wondering, and one person did ask it in one of the classes about, well, Mr. Miller, why did you pick the right hand method? Why didn't you use the left hand method? And there is a very good reason for that. If I had done the left hand method for this exact example, all of my boxes would have been above the curve, right? So that would have changed this inequality, which is fine. It's not a big deal, but it's not going to give me any more information, because all that's going to do is say that my series is greater than a convergent integral, but that doesn't mean that my series is going to converge. If this converges to 2, let's say, like we found, and this is bigger than 2, well, it could be 5. Okay, that'd be okay. Could be infinity. I have no idea. All I know is that the series is bigger. So we purposefully picked a method that would give us a definitive answer. Okay, so let's actually do an example of going the other way. Let's actually do an example where we are above the curve, and we'll see how that does help us too. It just doesn't help us in this particular example. Okay, I'm actually going to stop the video here so it's not too long. You got one thing at a time, and I'll make another video separately for when we're above the curve. Okay? Let me know if you have any questions, as always.